alcohols. So, famous quote by a famous person. Let's see if you know this person. Alcohol, here's to alcohol, the cause of and the solution to all of life's problems. Who said that? Right, Homer Simpson. Okay. The only time in the semester I'll quote The Simpsons, but yeah, I don't think Homer had in mind all the applications of alcohol beyond beverages. Alcohols are very important solvents in industry, very important reagents, antiseptic materials, all the stuff in the sanitizing stuff. The main ingredient is ethanol, which has antibacterial activity, denatures proteins in microorganisms and kills them quite efficiently. So we use it for that. It evaporates quickly. It has a cooling effect. So you're familiar somewhat. I think on Friday I'll bring a bunch of alcohols and maybe we'll have a couple demos and do a couple things there. But let's get to the main event here. The most important reaction I think is alcohol dehydration. And here we're taking alcohols, tertiary, secondary, and primary, and removing what? The elements of water. So where do we remove here? Well, we got a hydrogen coming off here and the OH group. But we have to have a reagent. We have to have some conditions to make this occur. It doesn't happen spontaneously, of course. Amazingly, if we just add a catalytic amount of a super strong acid, sulfuric acid is the one we'll use. There are other strong acids that will do this. But be careful, not the halogen acids. The halogen acids later on will do something else. They'll halogenate alcohols. So we're not using HBr, HCl yet. And those will give different products. So just a heads up there. We can also use this guy, tosic acid, which is also a sulfonic acid, but it's an organic soluble one. Okay, so a solubility issue there. It's the same kind of thing. It's got, the really resonance stabilized structure there, but it has this aromatic methyl benzene ring, which is called a toluene group. So tosyl, TS, it's not in the periodic table. There's no element TS. Don't look for it there. TS stands for paratoluene sulfonic acid. Okay. At least we draw the OH part here for that. And you see it there, right? This proton here can be donated. Resonance stabilized conjugate base, just like sulfuric acid. Okay. And then we get the alkene product here. It works for tertiary, secondary, and primary. Tertiary is faster than secondary. Primary is very slow, but they will go. They're different mechanisms. We'll get into that here in a second. And by Zaitse's rule, we form the more substituted alkenes. Now, all of the 9 beta hydrogens here are the same in tert-butyl alcohol, so you don't have to worry. Just rip off water, put the alkene there, and that's your product. The byproduct's water. We generally don't worry about that. We'll see in our mechanism how we can account for these two products and use our catalyst. Now, when we say catalyst, notice it's not consumed during the reaction. We use it to do what? To create a pathway that's faster in its speed and lower in energy for the rate limiting steps. So we'll see that. Let's do some other examples here. So here we have an ethyl, 2 methyls here on what this tertiary alcohol. So where are we going to put the alkene, our product? Yeah, we're going to put it over here to give a tri-substituted alkene, right? We're not going to eliminate water up here. That would be a di-substituted alkene. So again, examining the structures, and here we have a secondary alcohol. We could eliminate water here or here. And notice we eliminate here, we have the possibility of cis and trans isomers in the alkene. So we will get the more substituted alkene on this side and the more stable trans stereoisomer. Okay. So a couple things there that come out of these more complicated examples. Here's a secondary alcohol like this one. It's slower in its reaction. Both sides are the same. So we go to cyclohexene from cyclohexanol. Okay. Yeah, you should know how to name all these alcohols. We could review that IUPAC naming. Relatively simple, right? Alkanols. Take the E off the end, add OL. Anybody want to review that? We could do that. Look back in your notes there. It should be okay. And then we got this one, 1, 2, 3, 4, 1 butanol. If we do that, it is quite slow, but we can get this product here, butene. Okay. Questions on any of those? Wide variety of reactions. Let's get into the mechanism. Our mechanism has some variations to it, but I think you can see that it's going to start out just with some acid-base chemistry. So here's sulfuric acid. And what are we going to do there? If we don't add the sulfuric acid, nothing happens. Alcohols are very stable on their own, right? But if we add the super strong acid, things happen. So what can we do here? Well, this is a super strong acid, right? So it has a pKa of like -4, -5, very strong. And our lone pairs here can grab that proton. So you don't see the proton, the H plus explicitly, but you should know that this is coming off as what? H plus, okay? In fact, if you do the mechanism and just show H plus and have the alcohol grabbing it, getting protonated, that's fine, okay? But the direction of the arrow and how that's drawn is important, right? So let's see, we go to the protonated alcohol, and I'll just draw it like that. And our byproduct at that point is what? HSO4 minus bisulfate, okay? The counter conjugate base of that. And that is actually favorable. In fact, we could do a pKa analysis and see that this equilibrium is favored. Why? This pKa is what? -4. This pKa hydronium ion is -2. Okay? So we are going to the weaker acid here. We're using the stronger acid to protonate. This is a favorable step. Okay? Now, once this forms, what can happen at this point? Our byproduct is what? Water. And you see it already, right? Here's H2O. What do we need to do to form water? Well, just break this bond, okay? We push the electrons out there. We've converted the alcohol from a terrible leaving group into a good leaving group, right? Why is it good? Because now the conjugate base of this is just neutral water, right? Not hydroxide if we try to break the bond here directly, right? We talked about that in the intro. So if we break the bond there, what do we get? Carbocation and water. Okay. So we've already got one of our products. It's a byproduct. You can kind of see how we're going to get to the alkene. We've got to break now a carbon-hydrogen bond at the beta position, right? So what do we need to do next? We need to come up with a base to take this proton off and flow these electrons in to form the alkene now. So that's kind of clear. The only thing left to do is to choose what base is going to take that proton off. So we've got a couple choices here. How many bases do we have here? Who can identify a base for us? Yeah. Okay, we've got bisulfate pointed out here as a base. How good is that base? Is there another base up here? What else do you see? There is one more base here. H2SO4 though is there. It's minus charge. Yeah. Water. Yes, so someone points out water here. In fact, we can analyze this and see which one might be best. If you use either one on a quiz or a test, we'd be okay with it. We had a choice before. We were doing some reactions in chapter 8 where we could either use chloride or water as the base. And I pointed out in class, I think that water is actually a better base. If we use the bisulfate, we'll actually go back to the catalyst, sulfuric acid. And that's okay. But yeah, if we use water here, what will we get? We'll get hydronium ion as a byproduct. But then you could say, well, sulfuric acid could reform by taking this proton back off, okay? But that's okay. This is a strong acid now. Its pKa is -2. That could actually function as the proton source for more alcohol, okay? So any acid that you form here as the byproduct, either using H2SO4 or water, will get you back to acid. And there's your catalyst, right? So that can do more reactions. And eventually all you'll get to is the water. It will build up. And as the reaction goes on, it's actually more likely that water will function as the base. Okay. But that's a little detail of the mechanism. The key thing here for you is to recognize we need to protonate the alcohol first, hydronium ion. And we need to form what? The carbocation. And that's really the key here. And you can already see why tertiary is faster, right? The stability of the carbocation. Tertiary is more stable than secondary, more stable than primary. So secondary will be slower, but it'll be the same mechanism. In fact, we call these two substrates here what? E1 type mechanism, okay? Why? Because it's going through this unimolecular ionization step, similar to what we saw before for the SN1 and the E1 reactions, okay? We have the carbocation intermediate. But this one is different here, okay? Primary. Let's look at primary. And the mechanism will be a little bit different, okay? Let's see. First of all, the rate here for these reactions will depend upon some rate constant times the concentration of hydronium ion. But you see that first step is complete protonation. Why? Because it's a strong acid, okay? So it only depends on this. So yeah, it has E1 or SN1 type kinetics that you can see there. All right, let's do primary. This does work. What was the one we had? Yeah, this guy, sulfuric acid, and we go to butene. And again, that's the second level of understanding, reactivity. What conditions, what starting material give what product, okay? So keep that separate from the mechanism. But no, bring them together, okay? Use the mechanism to help understand what's going on. So let's do it. Same thing here. We're going to protonate. But now the difference is hydronium ion on a primary. So you could think, well, we'll just ionize off water and give our carbocation, eliminate the beta proton, and we're good, right? Nope. What's the problem with that mechanism now that we just did if it's primary? What's the big problem? Yeah, the stability of the carbocation. So it's not going to go through that, okay? So what happens here is you have to have bisulfate or water as it builds up, okay, function as a base in a bimolecular type reaction, okay? So this will actually depend upon the concentration of this. You don't need to worry about that. But what it does is directly take off the beta hydrogen. It kind of looks like the E2 elimination, right? We've got a better leaving group now. And then we have a base. These are lousy bases, right? This is not TB toxide. But with primary they go. They're very slow, but it's got to wait around for some base to pull off the proton at the beta position and then go directly to this. And you see that generates the catalyst again, right? Then you have hydronium ion, and that can go back and protonate more alcohol and bring it over. Okay. Now, there's a problem here with these reactions in general. If you look at the bonds that are broken and the bonds that are made here, there's a problem. Okay, we're making an oxygen-hydrogen bond, which is good, okay? Let's look at the bond dissociation energies. That's, about 100 kcals per mole. That's good. That's a good driving force, we would say, for this reaction. It's negative energy, right? So that's making it exothermic. And what we're getting a pi bond, which is about 60 kcals per mole. But look, we're breaking what? We're breaking a carbon-oxygen bond, and we're breaking a carbon-hydrogen bond. Okay. Both of those are very high, okay? 90 or so kcals per mole. This one's about 60. This one's about 100. If you add this up here, delta G is actually what? Not negative. It's not exothermic. It turns out it's endothermic. Okay, this is not favorable as we've drawn it. But I've been showing you these reactions. These actually work. Okay, so what is the deal here? Well, K, the equilibrium, we can draw this for any reaction, equals what? The concentration of the product, which will be the alkene, and water, And, these brackets mean molarity. These can be measured. And over the concentration of what? The alcohol. So what can we do to this equilibrium in order to make this reaction favorable? We want this product, right? So what can we do here? Well, we can eliminate water, okay, or dehydrate it or distill it, and that will increase what? By Le Chatelier's principle, the concentration of that. Because we've got to keep K, which actually isn't favorable, constant, right? Okay. So even if we have a reaction that's not favorable, if we perturb the equilibrium or provide a shock to it, it will respond in such a way to make more of that. There's not much we can do here, adding more of that, or adding more catalyst. If we add more catalyst, it'll just go a little faster, okay? Just get to equilibrium faster. The key thing here is either distilling the water, that is a boiling point of 100 degrees C, that's pretty high. Most of the small alkenes have lower boiling points than that, and a lot of times we just heat this up distill out the thing based on the boiling point, okay? This material comes out of the equilibrium, and that just draws more over from the left and makes more of the alkene product, okay? I'll show you those numbers. Let's go to the overhead real quick there again and see, what did we have there? Oh, there it is. Okay, so I like this graphic in your book. There's the key reaction, just dehydrating ethanol to go to ethylene. So that's simple. These bond dissociation numbers come out of the book. Oh, sorry. They're in kilojoules per mole. Ouch. Okay. Here are the bonds that are broken. The carbon-oxygen bond, like I said, carbon-hydrogen bond. Yeah, they're both 90, 100 kcal per mole. So that's quite a bit. Okay. That's a big positive number. And look, the alkene here, yeah, if you divide by 4.187, you get about 60 there for the alkene, you see. And you're making a oxygen hydrogen bond on water. That's very favorable. That's over 100 kcal per mole. But you see, you add that up. Here's your negative energy that's coming out. These are the bonds you're making, right? It's always a function of, the bonds you're breaking versus bonds you're making. So then you add these two up, and what do you get? A positive number. Divide by 4, it's about plus 9 kcal per mole. So it's an endothermic reaction, right? If you look at the bond association energies. But it can work, okay? So Le Chatelier's principle is kind of a key thing to keep in mind there. All right. Now, if this was it, alcohol dehydration would be relatively simple. Sorry to say it's not simple. Just when you think you have it down, we're going to throw a fly in the ointment here, which is going to be rearrangements, okay? These are carbocations, and they can rearrange from a less stable carbocation to a more stable carbocation. Let me show you what I mean there. Rearrangements. And I'll give you a key that you can always cue on to figure out whether it will do a rearrangement or not, okay? Well, let me first give you a reaction. Here's a secondary alcohol, which can go just fine, H2SO4. And, by Le Chatelier's principle, this will go. And where can we put the alkene? Well, you only have beta hydrogens right here to eliminate water. And so you might think that that should be the product. Okay? Well, sorry, that's not the product. The product actually turns out to be this. Okay, now did I misdraw something or not keep track of the carbons correctly? Because this carbon over here, you could say is a terbutyl group, right, with 3 methyls on it and a quaternary carbon. How did we go over to this? What happened to this? There's obviously a change that's gone on here. It's undergone a rearrangement, okay? And when we say rearrangement, what we mean to say is at the beta position, if you have branching, you can always go to the more stable carbocation first, okay? And it will do that by moving an alkyl group, shifting with its pair of electrons, or a hydride group, with its pair of electrons. And so you can kind of see what shifted here had to be one of those methyl groups. So it's not too bad. Let's use the mechanism to try to figure out why we went from this expected alkene, which turns out to be not the product, okay? And it gives all of that. In fact, 100% of the product in this case is this product right here. So what happened? Let's go ahead and protonate. So hydronium ion, use the principles, acid-base chemistry. That's going to be favored, going to be downhill. It's going to give that new, weaker acid, you can say. Okay, and it is secondary, so let's go ahead and form the what? Carbocation. So there it is. And what type of carbocation is it? It's indeed secondary. But that's not the product. Yeah, we could take a proton off here and go to this product. But what are we going to do instead? Well, we can take this methyl group right here and shift it. We call that a 1-2 shift. Okay, it's a specific type of rearrangement. And why are we shifting that? Well, this is a secondary carbocation. If we do the shift, what's going to occur now? There's our methyl, and let's label that CH3. Okay, these are also CH3 groups, but I'm labeling this one here. And you can see it moved over with its pair of electrons. Okay, so this is a methyl shift. Okay, so I'll draw the electrons there. It's not a free anion. Okay, you could just say it's an extreme of hyperconjugation, right? We talked about the stability of carbocations. Well, this is just lining this sigma bond up with this empty p orbital. We could analyze the molecular orbitals a little bit there. Why would it shift? It involves breaking a carbon-carbon bond and making a carbon-carbon bond. So it's thermoneutral. It's not exothermic or endothermic. Well, what is it doing? It's going downhill to what? A more favorable carbocation now. When this CH3 group moves over with its pair of electrons, it now vacated that carbon and left what? A dearth, a lack of electron density there. And if we count up the formal charge, right? We go from a plus charge here, the secondary position, and now what's this? Not secondary anymore. What is it? It's tertiary. Okay. And that's favorable by at least 10 kcals per mole. Okay. So before the beta hydrogen can be pulled off, and that's a bimolecular event. We have to organize the base there, grab the proton, and form the alkene. Instead, what's faster is this shift within the same molecule. That's an intramolecular event. It's happening within the molecule and just going downhill to the more stable intermediate. Okay, so it shouldn't be too mysterious. And the way you deal with rearrangements, and they can be somewhat perplexing, but there's some simple examples we expect you to know. If it's a harder example, look for branching at this beta position and examine the carbocation intermediate and think about what could occur that would make this pathway more favorable. And certainly going through this tertiary spot, oh, we're not done yet. Let's get to the product. So what do we need to do? We've got this hydrogen here we need to pull off. Let's use water, pair of electrons, take the proton off, dump them down there. And you see that goes directly to the product. So not this, sorry, okay. This is your product from this simple branched alcohol, okay. Questions on that? The new thing here is right here, right? The shift. But that should make some sense. We're going from a secondary carbocation to the more stable tertiary with just a simple movement from one position to the other. This indication here is just a mechanistic marker. You could say this is the one position, this is the two position within that mechanism. Okay, it's not the nomenclature numbering, but it shows that from an adjacent carbon over to the other one. That's what the 1-2 shift means. There are other types of shifts. The ones we'll see will be alkyl shifts, like we saw here with this methyl, and hydrides. Okay, so let's do some other examples, and hopefully this will make some sense. Let's see. Yeah. So what do we got? Let's get some more room here. So yeah, if you work enough of these examples, it'll make some sense. The simple ones, you can usually see it pretty easily. Some of these, if they're a little more complicated alcohol, it's kind of hard to see what might occur here. So here's sulfuric acid, again with a secondary alcohol. So by Zaitsev's rule, you might think, well, we should form this, which would be the tri-substituted alkene. That turns out not to be the product. Guess what? This turns out to be the product. Okay. How do we get that? Well, let's see here. What kind of shifts can we do here? Well, we've got, oh, hold on. Had that wrong there. Okay. Yeah, you might think, well, oh, had that methyl in the wrong place. So you might think that this would be the product, right? So that would stay there, and that would be the alkene product, okay? Sorry, got to modify your notes. But this is the correct product there. Had the methyl in the wrong spot. Okay, so if this alcohol, secondary alcohol, but it does have branching next door, right? So it is branched there. So that's kind of what you look for at that beta position and wonder about that. Okay, so it's not going to be your typical dehydration just on the localized position there with nothing else going on. The carbon framework is now undergoing a change. We haven't seen that before. SN2, E1, E2, all those reactions, we always kept the carbon framework static, right? But now with these rearrangements, something's obviously changing within the carbon framework. So let's see if we can do this. Let's go ahead and protonate here. And what do we get? We get the hydronium ion. And it is secondary, so we would go through a carbocation. And get that. And you see, that's maybe where we'd expect the dehydration to occur then. But what can occur here now? A shift, right? The alkyl group can move over. And we get an isopropyl out here now. And the tertiary carbocation right there. So it's again going from secondary to tertiary. And now Zaitsev's rule still applies. Which proton are we going to take off? Well, it's going to be this one. We've got beta hydrogens here and here. Those would give tri-substitute alkenes. If we take this off with water or bisulfate, then we're going to go to this. Okay, so that's our product, not this right here. Okay, questions on that? Again, it's an alkyl methyl shift here that's going on to give that product. Okay, let's do another one here. Question? No? Let's do one that might not involve an alkyl. How about a hydride shift? So here's a similar type of starting material, sulfuric acid, and we go to this. Two tri-substituted alkene products. And here, you might think, well, this would be your standard one, okay? And if we just protonate and what? Form the carbocation. So there I'm doing a couple steps, right? And if we think about, well, and then we'll just lose this off with the base, right? That goes to that second product there. How do we get this product? That's really the question. Instead of just having the base take that off and do the dehydration, what else could occur here? This is a secondary carbocation, and there is branching here, okay? Granted, there's a hydrogen and then two alkyl groups at the beta position, right? So it's a little bit different. But let's take that hydrogen and have that move over. So this is a hydride shift now, okay? So if this hydrogen moves over, look, we go from a secondary carbocation to what? A tertiary carbocation. So, yeah, let's label that hydrogen now, okay? And you can see that should be more stable, and that's a fast step. And let's see, there's actually, both of these are actually obtained in this reaction. This one's 80% here. This one's only 20%. So there's where it's a mix, okay? And this would be a harder problem to analyze, but I think you can do it, right? If we shift this over here, what do? Then we've got hydrogens here and here, which are really the same position here, and then have water take off that proton. You see that goes to the major product, okay, via that hydride shift, okay? So some other things can go on. What you can always say is if a shift occurs, it's going from a less stable carbocation to a more stable carbocation. And that's always a hallmark of these rearrangements. But it can be somewhat perplexing. Okay. Let me show you one here that's quite a bit more complicated. But I think we can analyze it. At first, it might appear to be kind of a shock here. Let's have a cyclobutane alcohol. And we're going to acidify here, catalytic sulfuric acid. And you might think, well, the trisubstituted alkene product. By Zaitsev's rule, that should be good. It turns out there's none of this obtained. Okay, the only product is this, 100%. So it's obviously a rearrangement of the carbon skeleton, right? Something is significantly, fundamentally changed. What have we done? We've gone from a 4-membered ring to a 5-membered ring, which should give you kind of a hint here what's going on. This starts out as what? Very strained. This theta angle being 90 degrees. Okay, that's going to have a lot of energy associated with it. So let's go about this using the fundamentals of the mechanism and see if we can figure this out. So this is indeed a 1-2 shift. It's an alkyl shift. And indeed, we'll see again, it's a less stable carbocation going to a more stable carbocation within the context of relief of this angle strain, okay? So let's go ahead, protonate. What do we get? Hydronium ion. Okay, so you see the commonality there. And you could think, well, if we just ionize water off here, we'll have a secondary carbocation, okay? Let's go ahead and do that. So yeah, a lot of the mechanisms are the same. And yeah, and if we take this proton off and put the double bond right there, we get that. But you're told, nope, not going to happen. What else can happen here? We've got a secondary carbocation. We could think about hydride coming over. That would give us a tertiary carbocation. What else could occur? Let's take this carbon-carbon bond and move it over, okay? So that's an alkyl shift. It's not a methyl shift, it's really a methylene, but it's going to what? Do the theta angle relief here. Let's see. So let's draw that there. And our carbocations over there. So I just took this bond and moved it from here over to here, okay? There was this secondary carbocation right there, but by shifting that alkyl over, I go to this. But wait a minute, what type of carbocation is this now? It's still secondary. Why would that be favored? You go from secondary carbocation to secondary? What's the main issue here? What's the driving force again for this reaction? Yeah, it's the angle strain, right? Here you had this highly strained thing, 90-degree theta angles. And now what? You have a 5-member ring. Yeah, I drew this kind of flat. I kept the same geometry there. Let's redraw this, okay? So what should that really look like? Well, it will look like that, right? Okay. And you could say, well, okay, we can then shift here to go from the secondary over to what? Over to the tertiary, okay? There's our hydrogen there now. But we're just going to take that hydrogen off anyway, right? So what? And we got the same ones over here as here. So yeah, water taking that proton off gives that, okay? But the main thing, and the reason why it goes at all, is what? now you have this strain-free. It's a 5-membered ring. These internal angles are actually 108 in a cyclopentane. So that's going to be highly downhill. In fact, it's downhill by about 30 kcals per mole to relieve this angle strain. So going from here to here, very favorable, and then you get the dehydration completed there. Okay, but yeah, fundamental change in the carbon framework. But I think the principles hold here. Branching at the beta position, yeah, it's there. But now we have the angle strain issue, and then shifting over here to give the carbocation. Then initially you'd say, well, secondary from secondary. That shouldn't go. Those are the same energy. But look, this is strain free now, right? And then you can eliminate that one directly to go to that, or do this shift first if you want. And there you see the tertiary carbocation. Okay. Anyway, question on that one? Yeah, that's a little bit tricky one there, but I think we're okay on that. Let's show a couple other reagents here that can do this. These acidic conditions are often a problem, and if the rest of the molecule is not stable to strong acid, use of sulfuric acid or tosic acid is often not a good option. We can also do dehydrations with this reagent, PlCl3, or phosphorus oxytrichloride, and pyridine. And pyridine is this heterocyclic amine base. It's not a super strong base, but it soaks up HCl that might be present in the substrate. So you can take secondary alcohols. In fact, it's really good for secondary alcohols. Tertiary sometimes. Primary will often lead to substitutions instead with POCL. It really is only limited to secondary to be really useful. I'll show some of the mechanism and how it's useful. Well, let's just look at the reactivity first. So POCL and pyridine. And we could do that with sulfuric acid, but notice neither of these reagents is an acid, right? This is not strong protic acid now. So this is a complementary type of conditions which allow us to do these reactions not under carbocation forming conditions. And guess what? The nice thing here is no rearrangements. So if you want to do these substrates, and I'll put them back up there, the different mechanism, non-acidic conditions, POCL now will let us do dehydrations and give us the Zaitsev alkene, even if there is branching with no rearrangement, which is kind of cool. But let's look at this one. So we can go from cyclohexanol, cyclohexene, no problem. Butanol to butene. Yeah, and you see that's the Zaitsev thing. And then this one, the one we just did here with the rearrangement, right? If we did that with sulfuric acid, we had the methyl migration, and we got the tetrasubstitute alkene, right? With the methyl shifting over. But now with POCL, okay, these are all conditions with POCl3 and pyridine. What do we get here? We get the alkene with no rearrangements. So that's kind of cool. And this one, I think we had this one. Oh, well, this is a little bit different from that one. But you see you got a lot of branching here next door and a lot of rearrangement possibilities. But with POCl3 and pyridine, we get that product. Okay. I'd like to just show the graphics from the book to do the mechanism here. This will convert the alcohol into a good leaving group. And then there is a base, that's going to take that beta proton off, which is going to be pyridine. Okay. I don't expect you to know the mechanism of this. This gets a little complicated, especially how this is converted into a good leaving group. It starts out with the lone pair on the alcohol actually attacking the phosphorus. If you draw this reagent out, POCl3, it looks like this. Phosphorus is right below nitrogen in the periodic table, so it has 5 valence electrons. Because it's lower in the periodic table, it can exceed the octet rule. So you've got what? You've got 5 bonds here, so that's 10 total electrons. And you can see here with all these electronegative chlorides here, the mechanism of how you get to the better leaving group is this. It attacks the electron deficient phosphorus with all these polar covalent bonds here. And eventually one chloride comes off. I don't expect you to go through that mechanism. Let's go to the graphics in the book and maybe just look at that. Yeah, there it is. Okay. Yeah, I like this. Okay. This one's a good mechanism. And I've never put this part, the mechanism part of this dehydration on a quiz or a test. You need to know the acid catalyzed dehydration mechanistically and what's going on there. But here for Pockle, no. So this converts it into the phosphorus oxydichloride leaving group, you see. And there's pyridine doing its thing, taking a proton off there. And it is a mild base. It's organic soluble. So pyridine's good in that regard. Take the proton off. And it goes to this. So this is the phosphorus oxydichloride leaving group. This is not an alcohol now, right? So this reagent is consumed. It's not a catalyst. So you have to invest some effort here with that. But yeah, so that's the leaving group. Pyridine just stays as pyridinium cation. That's just a byproduct now. We won't worry about that. And then here's the thing. You have to have excess of the pyridine. Usually we put in 3 to 5 equivalents. It's no problem. And then what? Pyridine just grabs that proton off. There's no shifting here, okay? There's no free carbocation. You need the carbocation to do the rearrangement, right? So this mechanism's very different than the acid catalyzing where we saw carbocations. But here, you just form the new leaving group. And you couldn't directly eliminate an alcohol because that would have hydroxide coming off as a leaving group. That's a very strong base, okay? It's not a good leaving group. But if we make the phosphorus oxychloride thing here, this guy, then that is a good leaving group. And even though pyridine's not a real strong base, the pK of protonated pyridine, pyridinium cation is about 5. It's about the same acidity as carboxylic acid. And so you can grab that proton mildly, flow the electrons. Notice how the electrons are drawn, the flow of electrons. And then there's our new double bond. Okay. So we'll leave it at that. I don't expect you to know that mechanism, but at least understand it being fundamentally different from the dehydration reaction. Question on this mechanism here? Hopefully you could see my cursor okay, pointing through that. Here's some applications of it. Well, this is a couple things. So here we're showing tosic acid with a tertiary alcohol. So that's like sulfuric acid. So that's the dehydration under acidic conditions. Tosic acid is also a strong acid, okay? We use it as an alternative because this is a relatively nonpolar reagent. We have to put this in a nonpolar solvent. And sulfuric acid's very polar, so it's not compatible. But the tosic acid you see with that benzene group, right, is nonpolar. So that tends to be more organic soluble. Tertiary alcohol, there's our elimination right there, the Markovnikov product. It's a tetrasubstituted alkene. This is on the pathway to make vitamin A, which is made industrially on very large scale, used for a lot of medicinal and topical dermatology applications, vitamin A. You see that bond right there with the tosic acid, catalytic amount, loss of that elements of water right there gives the thing there. There's another step here. This hydroxide takes this ester off. We'll learn about that later. So the hydroxide here is not involved in the dehydration. Okay, some people ask about that, but yeah, it's a separate step. This acetate ester coming off. All right, and here's another one. Tertiary alcohol again, but now we're using Pockle. This framework here is sensitive to strong acid. So instead, we're using phosphorus oxychloride and pyridine, and it forms the double bond right there, which is trisubstituted alkene right there. And it's a couple steps. We go to patchouli alcohol, which is in pistachio nuts. And this intermediate's also been used in the synthesis of Taxol, the anti-cancer agent. So this is kind of a famous little intermediate, patchouli, kind of a funny name. And it's a couple more steps to make that. The key step here is the Pockle, cleanly doing the dehydration under non-acidic conditions, okay? So that type of thing we'd expect you to know, the reactivity. But again, not the mechanism of Pockle, okay? I think we'll leave it there on that. Oh, and thionyl chloride, phosphorus trichloride. That's going ahead now. The next reaction we're going to learn, I think that's it for dehydration. We will summarize that at the end of the chapter. Let me just give you an intro to the next type of reaction, which is going to be halogenation. So we're going to be able to take alcohols, whatever they are, and halogenate them, convert them into alkyl halides. Chloride, bromide are the common ones. Fluorides are made differently, iodides also. Iodides generally are not as stable as bromides or chlorides, but that's a very important transformation to halogenate an alcohol. And we're going to do it with HX, okay? And that will be strong conditions. These are strong acids. And look, we're going to go through carbocations. And then we're going to have complementary reagents that don't go through carbocations, that do the halogenation cleanly under non-acidic conditions. That'll be thionyl chloride, SOCl2. It's kind of related to POCl. It's the oxide dihalide of sulfur now, not phosphorus. But thionyl chloride here will cleanly take it to the chloride without rearrangements, and it will do it with secondary, with inversion of the stereochemistry. So there's a little bit on the mechanism there. Or if we want the bromide, we use phosphorus tribromide, and that will form the bromide cleanly from the alcohol. So stay tuned for this, read ahead. And then there's the last couple of topics in here in this chapter concerning the ethers, and I'll show you some applications of those also. But a number of reactions here, right? Dehydration with acid, dehydration with POCl, and then halogenation with the halide acids, and then with thionyl chloride, phosphorus tribromide, and then a couple reactions on ethers. Okay, so you see there's quite a few reactions in this chapter. And we'll see that in the next couple chapters too with alkenes. So yeah, get good at this, recognizing reactivity and then supplementing your understanding with the mechanism. That's really the key to getting through these next couple chapters. So we'll leave it there.